Hey, science learners, and welcome to our second half of our conversation about the chemistry of acids and bases. Last video, I basically described to you the differences between acids and bases and the amount of hydronium versus hydroxide that determines if a solution is acidic or basic. I mentioned a couple of times in the last video a unit of measurement known as pH, and pretty much I'm assuming everyone here has heard of pH. It's been a topic of conversation in earlier science classes, but we're going to delve a little deeper into it today and basically discuss how you can calculate the pH of a substance and using mathematics. So first of all, what is pH? Well, it's a way to measure the amount of an acid in a solution. That's basically what it is. And it was developed in the early 20th century, this form of measurement, by a scientist by the name of Søren Sørensen. And there's been a lot of speculation as to what pH means. There really has never been a definitive answer to this, and there's a lot of speculation. But most people believe that what Sorensen was trying to mean, I guess, with the use of pH is the power of or the potential of hydrogen. That's what that's what pH apparently means. And you know probably the basics about pH. You understand that it has to do with the acidity of a solution, and it's basically a way to specifically measure the concentration of hydronium in a solution. So that's what the pH scale is used for. There is another scale, by the way, that's out there, and we're not going to discuss it heavily. It's in one of the videos I'm going to let you look at today, but there is also what's called the pOH scale as well, which is the power of hydronium, of hydroxide. So that scale measures the amount of hydroxide that is in a solution. But we're dealing with pH, which is hydrogen, which is AKA donating the proton, which it means AKA we're getting hydronium ions. So the pH scale indicates the concentration of hydronium in a solution. Now, this is going to be a repeat. You know the pH scale is from 0 to 14. That's the scale. There are no units for pH. pH is simply, you would just write down pH equals 5.7. There are no units for pH. And you should know this already, but a pH of less than 7 is acidic. A pH of higher than 7 is basic, and a pH of exactly 7 is considered to be neutral, which would mean that you have equal amounts of hydroxide and hydronium ions in the solution at that point. A pH of 0 indicates the absolute strongest acids, although you saw in the video in my last video, if you did watch that little link to the strongest acids known to man, there are actually acids that are below 0 on the pH scale, but for our purposes, we're going to say that 0 for the standard acid that's out there is about as strong as you're going to get, and then 14 would be the absolute strongest bases. Would be 14. Another thing you got to remember about the pH scale is it's like the Richter scale, which measures earthquakes. It's a logarithmic scale, which means that every number represents an increase of 10 times the intensity. So, for example, if I have a pH of 7 and I have a pH of 6, the pH of 6 is 10 times more acidic than the pH of 7. If I have a pH of, say, 14, and I have a pH of 10, well, that would be 11, 12, 13, 14. So that's 4 multiplications of 10. So that'd be 10, 100, 1,000, 10,000. So if I'm going from 10 to 14, it would be 10,000 times more basic if I was going up. I'm going up from 10 to 14. Although you could also argue that 10 is 10,000 times more acidic than 14. That could also be a way you could discuss that. And there's a few more examples here on the notes that you might want to take a peek at, but pretty much for every number you go up, you're multiplying by 10. So if I go from, say, 5 to 8, it's going to be 6, 7, 8. That's 3 zeros. I got an increase of 1,000 times. If I'm going up to 8, it's going to be 1,000 times more basic. If I'm going down from 8 to 5, it's going to be 1,000 times more acidic. So that's how you calculate the magnitude of acidity or the basicness of a solution. Lots of common products that are in our households that are either acidic or basic. If you're going for acidic substances in your household, you can look at battery acid, vinegar, orange juice, tomatoes, black coffee. If you're peeing, urine is also slightly. Hopefully you're all peeing, because that would be a bad sign if you weren't. But it's slightly acidic as well. On the basic side, you've got things like seawater, baking soda, antacids that are neutralizing stomach acid. Ammonia, we talked about last day, is a very strong base. Soap is a base as well. Bleach, drain cleaner, these are all examples of bases. And you can see that the further away you go from 7, either this way toward the basic side or this way to the acidic side, the further away you go from the middle, the more extreme and the more powerful either the bases are closer to 0 and the bases are closer to 14. But how do you calculate the actual pH of a solution? Well, as I mentioned, pH is a measurement of the amount of hydronium that is present in a solution. So there is a formula that we use for this, and the formula is, if I'm trying to calculate a pH of a solution based on the concentration of hydronium that's in the solution, I'm going to use this formula. And this formula is on page 11 of your data booklet. Let me just pull it up right here, page 11, just so you're not thinking I'm making this stuff up. Here's your pH formulas right at the bottom of the page. They're both there. I'll be discussing both of them today. So in this case, I've got a pH is equal to the negative log 10 of the concentration of hydronium. So the button you want to be using for these formulas is the log 10 button on your calculator. So and remember that the concentration of hydronium will be measured in these questions in moles per liter. That will be the concentration value that is assigned to the acids or the bases in these questions in order to calculate the pH of them. So for the example in your notes here, and hopefully you got your notes in front of you, and hopefully you got a calculator with you as well. Make sure if you don't have a calculator, grab your scientific calculator right now. You're going to want to maybe have it just to kind of make sure that I'm not just making up numbers here, that I'm just doing some voodoo science or something like that. But what we've got here is we've got a solution on this page that has a concentration of 6.7 times 10 to the negative 8th moles per liter of hydronium. Calculate the pH. Okay, so what I'm going to use my formula that I've got up here. pH equals the negative log 10 of the concentration of hydronium, which means that I'm going to punch into my calculator the scientific notation, which is going to be 6.7 times 10 to the negative 8th. I have to punch it in as actual scientific digits. Otherwise, this is going to be fairly difficult for you. And if you don't know how to do that, there's plenty of sites on YouTube that can show you how to do that, or potentially even ask me in class if you want to do that. In this case, if I take the negative log 10 of 6.7 times 10 to the negative 8th moles per liter, what I'm going to wind up getting is a pH of roughly 7.2. So it's just slightly basic, just above neutral in that case. With significant digits, pH doesn't really respond well to significant digits. pH, you can just basically run it out all the way. For our purposes, though, we can keep this a little bit simple. If you've got 2 significant digits, like in the case of this equation, we've got 6.7, so that's 2 significant digits there. I've just rounded it to 7.2. But technically with pH, the rounding rules are a little weird for pH, but just to make your life easy, just look at the question. If it says round it to 2 decimal places, or if it tells you to round to so many significant digits, just do that at that point. So, but that's how you calculate. Here's another example, and again, this is where your turn. Don't maybe skip ahead to the notes at this point. Again, if you've been given a hydronium concentration of 4.72 times 10 to the negative 11th moles per liter, calculate the pH. Give you a couple seconds. You can pause me right now if you want to try that out on your own. And here we go. This is basically what the breakdown is going to be. You're going to use our negative log 10 of the hydronium concentration. You're going to have negative log 10 of 4.72 times 10 to the negative 11th. That's going to give you a pH of roughly 10.3. 10.3 for that one. And the next one is going to be hydronium concentration of 3.54 times 10 to the negative third. Calculate the pH. Give you a couple seconds. You can pause me if you have to. You're probably loving this. Okay, here we go. So if I have this, I'm going to take my negative log 10 times, my negative log 10 of 3.54 times 10 to the negative third is going to give me roughly a pH of 2.45. There are 3 significant digits in that number, so that's why we rounded to 2 decimal places rather than 2. One thing you're going to notice, and this is a great little thing to remember when you're doing these equations, you will notice that as the concentration gets bigger, when that negative number beside the 10 gets smaller, that means we're getting closer to a value that is 1, right, or 100%, right? When we're getting closer to that number, like the number that was 3.54 times 10 to the negative third is much larger than, say, the concentration of the first one, which is 4.72 times 10 to the negative 11th. There's way fewer hydronium ions in that concentration than there is in the one at the bottom. You'll notice that as the concentration of hydronium goes up, the pH is actually getting smaller. And that makes sense because acids, we've mentioned, acids have pHs of below 7. They produce more hydronium. The stronger the acid, the more hydronium, the stronger the concentration of hydronium. When you use this equation, you're going to get smaller numbers. And so that actually works, for what we know about acids. So if you can remember that if you see a smaller number, there is a kind of a pattern to this, that as you begin to see larger numbers of hydronium ions in the concentration, you can pretty much predict that your numbers for your pH are going to be smaller. And the lower the hydronium concentration is in the solution, the higher that pH value will work out to when you're doing your calculations. But again, the little trick, make sure you got that negative number, that negative. You have to negative the value going in. Otherwise, you are going to run into some major trouble. And I would recommend right now, even if you have your calculator, run these numbers through with your calculator and just make sure that you're actually inputting that information correctly. Because if your numbers aren't matching what I've got here, then you're doing something wrong with your calculator, and you want to figure that out and figure out what you're doing wrong so that you're not making simple calculational errors that can be very easily avoided with these questions. Okay. So we've done how do you calculate pH from the concentration of hydronium ions, but let's flip that. Let's do the other equation now. How do I calculate, if I have a pH value, how do I calculate a concentration of hydronium ions? Well, for this, we're going to do something a little different, and we're going to use a slightly different key on our calculator for this. But essentially, the concentration of hydronium ions is going to be calculated using the formula 10 to the negative pH. All right, so to calculate this, you're going to use the button on your calculator that has the 10x button on it. There's the 10 with the little superscript of the x on there. That's the button you're going to be wanting to use. But again, there's a little trick. That pH has to be a negative value. So if I've got a pH of 7, I can't go 10 to the 7th because that's going to give me a number that's way bigger than 1. All these concentrations are going to be less than a value of 1. They're all going to be 5.5 times 10 to the negative something. They're all going to be 10 to the negative something. None of them are going to have positive values. So again, if I have a value of 7 for my pH, I would calculate it as I would enter -7, then hit the button. That's how I calculate it. Now, in the case of the formula here, we've got an example on your notes. Hopefully you're following along. You've got the solution has a pH of 5.3. How do I do that? Easy. I'm going to take 10 to the negative 5.3. So I'm going to type in negative 5.3, hit the button, and I'm going to get a concentration of 5.0 times 10 to the negative 6. And remember your units. pH doesn't have units, but concentration does. Moles per liter. That's the units you're going to need to use. Please make sure you show your units for concentration. Just because pH doesn't have units doesn't mean the concentration you can get away without having units. You have to have units for concentration. Let's do another one. Okay, here's a couple you can kind of follow along. Try to maybe not look at the notes ahead of time or look away from your notes right now. What's the hydronium concentration of a solution with a pH of 10.33? Give you a second. Pause me if you need to. Well, here's what I do. I'm going to use the calculated formula. Hydronium concentration equals 10 to the negative pH, which means that hydronium concentration is going to be 10 to the negative 10.33, which means I'm going to calculate that using this button. I'm going to get a value of 4.677 times 10 to the negative 11th moles per liter. Now, I could have rounded that. Actually, I should have rounded that. That should have been rounded. I shouldn't have been rounded because there are 4 significant digits in the pH. I've got 10.33. That's 4 significant digits. So I'm rounding it to 4 significant digits in my concentration. So that is correct. Let's try one more. What's the hydronium concentration of a solution that has a pH of 3.1? Again, pause me if you need to. Here's how you calculate it. Again, use the same formula. You're going to punch it in as 10 to the negative 3.1, which is going to give you a value when you hit the 10x button. If you type in negative 3.1, 10 to the x, you're going to get a value of 7.9 times 10 to the negative 4 moles per liter. And again, what's the correlation? The higher the pH number, the lower the concentration of hydronium it should be. The lower the pH value, the more acidic the solution is, the higher the hydronium concentration should be. So in this, you can clearly see that the 10.33 pH has a much lower concentration of hydronium at 10 to the negative 11th, as opposed to the pH of 3.1, which has a value somewhere in the range of 10 to the negative 4th. So there's definitely a correlation that you can follow when you're doing these questions to see if you're doing them right. Quick review on how to use these calculations, on how you calculate pH. This video is also going to discuss pOH. You can ignore that stuff, but the stuff on pH and calculating pH is definitely worthwhile. So please give that a watch right now. All right, we're back. So I'm going to finish up here with a couple more things. How do we measure pH? Just checking pH out on ourselves without a calculator. There are many ways that you can calculate pH, and there's a whole slew of methods, and you know probably already about litmus paper. Blue litmus paper turns red when you put it in an acid. Red litmus paper turns blue when you put it in a base. A quick video here if you want to take a peek that's going to show you all the different ways that we can calculate pH using different types of indicators, which I'm going to be discussing right now. So again, litmus paper, very, very simple litmus paper. It's basically going to be just determining whether something is above 7 or below 7 or at 7. It doesn't give you a specific value. It just tells you if something is acidic or basic or neutral. It doesn't give you an actual specific value. pH meters are wonderful. As you can see here in the diagram, that's a pH meter right over there. They're just devices where you can put them in the solution. They actually measure the solution digitally. You need batteries. They're a little bit more clunky. They are expensive. They are a little bit janky. You got to take care of them. Otherwise, they can get knocked out of alignment pretty easily. There are also things called universal indicators. These are the ones you'd be using if you have a hot tub. You're doing your color test on the pH of your water in a hot tub. They're basically going to indicate ranges. So the color is going to change almost like a rainbow of color, and then depending on what the pH is, it's going to be anywhere between let's say a red and a blue, but it isn't just red or blue. There's a variety of like greens and yellows and oranges in between that are going to indicate some, maybe more specific pH ranges as opposed to just litmus paper. But what we want to discuss the most today are acid-base indicators, and this is what is going to be a good chunk of this unit as well. You're going to go to page 12 for these guys, and I'm going to bring this slide up in about 2 seconds. But here are your indicators right here on the bottom. This chart here are your indicators. They're on the bottom there. They're right below the relative strengths of the acids and bases that we discussed in the last video. And here's the data. Here it is right here for you, so you can see it. You're going to make use of this because there will be some questions that are going to come your way where you have to calculate the rough pH of a solution based on what these indicators are doing. Now, on the chart, you can see that. Let's take a look at the first one, for example. The first one on this chart on the very top is methyl violet, and it's got a pH range of 0 to 1.6, which means that when it's 0, the indicator solution will be actually yellow, and then once it hits all the way to 1.6, it will be blue. In the range in between 0 and 1.6, it will sort of turn from a yellow to a green and then to a full blue. So, for example, if I said, hey, a substance, if I put methyl violet in a solution and the color of the solution of methyl violet was blue, I know for a fact that that pH has to be higher than 1.6. It can't be below 1.6 because that indicator is blue. If I were to say methyl violet was yellow, you immediately know what the pH of the solution is. It's 0. It can't be anything lower than 0 because for our purposes there is no pH lower than 0. Give you another example. Let's go higher up. Let's go methyl red. Methyl red has a transition pH range of 4.8 to 6. Well, when it's at 4.8, the solution will be red. When it's at 6, it'll be yellow. So if I were to say, hey, I got a solution, I put methyl red in and it turns yellow, well, I immediately know that solution is going to be higher than 6. I know it's going to be higher. So it's got to be somewhere between 6 and 14. And then what they'll do is they'll throw in multiple indicators to kind of narrow the range down. So on this slide here, and I would get you to look at this slide right here, they're giving you 3 indicators that are listed. I got bromothymol blue, which is turning blue. I've got phenolphthalein, which is colorless, and I've got phenyl red, which is red. Estimate the pH of the solution. So based on this, I can go to my data sheet and simply look at them and say, okay, bromothymol blue is blue, which means that it's got to be at least a pH of higher than 7.6. Phenolphthalein is basically coming in at it's clear, so it's got to be lower than 8.2. So right now I know the pH is somewhere between 7.6 and 8.2, and phenyl red is red. Phenyl red is at 8. Okay, so I know it's got to be now, the 7.6 doesn't really matter. I know it's going to be between 8.0 and 8.2. That's my answer. That's pretty much just what I did. And here's the answer right here on the slide. Basically, I just walked you through it, how I would use my data sheet to calculate that. So basically, knowing those 3 colors on those 3 indicators is giving us an indication that the solution that we're dealing with is between 8 and 8.2 for a pH. That's it, folks, for chemistry of acids and bases. I'm going to give you some questions here to work on. I'm going to get you to complete practice questions 22 and 23 and practice questions 26 to 28, so 26, 27, and 28 on pages 183 to 186 of the textbook. As well, complete questions 1 to 2, questions 4, 5, and 6, and question 9 on page 187 of the textbook. That's it for today, guys. Thanks for tuning in, and we'll be back with more acids and bases next time.